Hello folks, so there are a lot of videos about these things called direction angles of a vector, and they do a great job of explaining, of using the formula and calculating it for you, but I've yet to find one that actually really explains it, and maybe I just haven't been looking hard enough, but that's what I want to do in this video, okay? So I have this nice diagram from our textbook, and here's what direction angle is. So the direction angles, so in 3 dimensions, there are 3 of these. I suppose in 4 dimensions there would be 4 of them, although the visual representation would be kind of lost on us. They're just the angles that the vector makes with the positive axes. So for example, the angle between the vector v, which is this blue one right here, and say the x-axis, the positive x-axis going this way, is going to be alpha right here. So there's a little bit of confusion I've seen where people think that it's just the angle between the positive x-axis and say the projection of v down into the xy plane. That's not what we're looking for here. This angle, if you were to like lay a protractor across it, would be not flat on the floor. Okay. Likewise, the angle between the positive y-axis and our vector v would be beta, so this one right here, and then gamma for the z-axis. In this video, we're just going to prove or get a formula for alpha, and a similar argument can be used to find beta and gamma as well. Okay, so the tool we're going to use to find this angle is the dot product, because that's what the dot product is great at doing, is finding the angles between 2 vectors. You could use the cross product, and we haven't talked about cross product yet, but the cross product, to get the cross product is like so much work already that it's just easier to use the dot product. Okay, so here's kind of my strategy here, is that if I can find a vector v, well, I have v, and this is going to look kind of weird, but oops, sorry. Let me start that over. If I have the vector v and I can essentially dot it with, well, the positive x-axis, then this would work, right, in theory. So I could calculate this because we know we have our easy peasy formula of just multiplying the corresponding components and then adding them. And then I can also evaluate, well, the quote-unquote magnitude of the x-axis, and you might see a problem with this already. And then multiply by the cosine of the angle, and then you could divide both sides by this, and then get cosine of the angle, and then take the inverse cosine. So this would totally work, except the problem with this is that the positive x-axis is infinitely long. So this on its own will not quite work. But I think the idea is sound. And so what are we trying to do? Well, remember that you don't actually need the entire positive x-axis. You really just need a vector that points in the same direction. Because, let's shorten this. Let's pretend I didn't have the positive x-axis, the entire thing, because that wouldn't make sense. It would be infinitely long. I just had maybe this vector, which lies along the positive x-axis, and its coordinates, or sorry, its components would be what? It would be some amount of x, so maybe like 9, 0, 0. It has no x, sorry, it has only x component, it has no y or z component. Well, it has a y and z component of 0. So yes, the dot product, the value of the dot product would be different depending on the length of this vector. However, the angle alpha is still whatever it is. It's not going to change. And so we can really choose any such vector that lies along the positive x-axis that we want. To make our life easier, I propose we use this really, really simple vector right here. And I'm going to use the vector 1, 0, 0. If you were going to use the same process to prove this formula for beta, then it would just be 0, 1, 0, and for gamma it'd be 0, 0, 1. Right? Okay, so we can actually do this now. Now notice that our vector 1, 1, 0 is simply the I unit vector, basis vector. So we'll just use that 1, 0, 0. So v, if I use, now let's pretend v is just ABC. So v itself is equal to ABC, and the vector that we're going to dot it with is the I vector, so that's just 1, 0, 0. So let's actually run this. Let's actually calculate this. So v dot I, is going to equal v, the magnitude of v, times the magnitude of I, and you'll see why this is nice, why we chose this, because this is going to be really simple, times cosine of the angle. or sorry, let's actually get a little bit more specific. Instead of theta, that's going to be alpha. Alpha right there. Alrighty. So, well, v dot I, that's going to be a times 1 plus, well, b times 0 plus c times 0. So that's really nice because that's just a. On this side, the magnitude of a is going to be, the square root of a, a squared plus b squared plus c squared. I'm just going to leave it as the magnitude of v, right? So no matter what v is, you'd be able to calculate its magnitude, no problem. The magnitude of I, notice, is just 1. It's just a unit vector pointing in x's direction, really. So I could just cross that off. It's just 1 times cosine of alpha. So if I clean this up, I really get a equals the magnitude of v times cosine of alpha. Do some rearranging here. We'll divide both sides by v, or the magnitude of v, rather. And then we get this nice easy peasy formula, actually, where cosine of alpha, alpha, oh, that's not pretty. Sorry about that. Cosine of alpha is equal to the a, so again, this is simply the x component of the vector that we're looking at, divided by its magnitude. And if I want to actually get, so this is the direction cosine. Some people will ask for the direction cosine. If that's what they're asking for. Or if they want the actual angle alpha, then the direction angle, again, this is the angle between our vector v and the positive x-axis. You just simply take the inverse cosine of that. And so you'd be taking the inverse cosine of a, the x component of v divided by its own magnitude. So it's seemingly kind of pretty complicated problem, but I think once we understand this principle right here, where the actual length of the vector we're dotting it with does not affect the angle, it's actually a pretty proof. Ready? So hopefully that makes sense. And now you can go out and calculate direction angles as you find fitting. Ready? Thanks for watching, and I'll catch you later.